Hi and welcome to another lesson in the physics video series. Today we're going to be talking about centripetal force examples with a constant radius and a changing speed. In the last video we had a changing radius with a constant speed, but today we're going to be looking at how a change in speed affects the required force to keep a car in the turn. Alright, let's get started. In today's problem, we're going to still maintain a car's mass of 1,000 kilograms, and we're going to have a 10-meter circle. However, we're going to start with a velocity of 10 meters per second, then we're going to double it, 20 meters per second. We're going to double that to 40 meters per second. We're going to see how the centripetal acceleration and centripetal force vary with this doubling of speeds. I've chosen a point here on the circle to show where the car actually is, and you can see that the centripetal force and the acceleration point towards the center, and at 90 degrees to both of them is the V tangent. You can imagine you're sitting in the car and this arrow is pointing in the direction that you're facing. Here I have the hand gesture showing the same, so that at any point on the circle you can determine the tangential velocity and its relationships to the centripetal force and centripetal acceleration respectively. We're still going to use the v squared over r formula, and we know that the v squared is now 10 meters per second. This is the variable that will change, and the radius is 10 meters. So we have 10 squared over 10, which gives us a centripetal acceleration of 10 meters per second squared. However, instead of changing the radius, we're going to change the speed. We're going to double the speed, and in doubling the speed, we're going to have v squared over r, but now the speed is 20 meters per second, and that's going to be squared. 20 squared over 10, that gives you 40 meters per second. So you can see automatically that when I doubled the speed from 10 to 20, I quadrupled the acceleration from 10 to 40 meters per second squared. That's because the relationship between acceleration and speed is a first power to second power relationship. That's a square. So if you double something and square it, that's quadruple. Let's take a look one more time. If we double the 20 meters per second to 40 meters per second, a sub c equals v squared over r. Take this 40, place it here, square it. 40 squared over 10, it's 160 meters per second squared acceleration. That is 4 times more than the one before it. So in summary, you can see that when I double the speed, I quadruple the acceleration each time. Let's take a look at what happens to the forces when I double the speeds. Now let's determine the centripetal force for each of these three speeds. We will use F equals ma, F sub c equals ma sub c, which is equal to m times v squared over r. The v squared over r was already calculated in the step above, so we'll take the answer here in the red box and we'll place it in the a sub c right here. So 1,000 kilograms times 10 meters per second squared gives you 10,000 newtons. So for a car traveling in a radius of 10 meters at a speed of 10 meters per second, 10,000 newtons is required to hold it on the turn. Now if I double that speed, which is what happens in problem number 2, we doubled the speed and therefore we quadrupled the acceleration. Multiplying that times the original mass gives us 40,000 newtons, which is in fact quadruple the amount of force. If I double the speed, I quadruple the acceleration, and I likewise quadruple the required amount of force. And if I double the speed one more time from 20 meters per second to 40 meters per second, we can see F equals mv squared over r, and we get 1,000 kilograms times the 160 meters per second squared gives us 160,000 newtons, which is quadruple of the value before it. So in general, we can see that when we double the speed, we quadruple the value of the acceleration and the required force. As I mentioned earlier, a driver has very little control over certain elements of the road, like the radius of the turn and even the amount of friction that's on a road, but the driver does have control over the speed. Say the driver was moving at 40 meters per second, which is quite fast, but he slows down. He halves his speed. Well, in halving his speed, he takes 1/4 of the force required to take the turn, and that's a much safer approach. So in conclusion, we can see that when we have a constant radius with a changing speed, the faster the speed, the more centripetal force is required to hold the vehicle in the turn. And sometimes there isn't enough centripetal force provided by the friction to hold the car in the turn. It's going too fast. He will proceed along the tangent. He will break the curve and will go flying off on a tangent. In the next video, we're going to discuss the time it takes to go around and how that varies the amount of centripetal acceleration and centripetal force. Thank you for watching, and we'll see you in the next video.